Now, if you remember from the very first lecture, we talked about there are two main purposes of getting z-scores. In particular, we want to compare individual scores to a population, and that's what we've done extensively up to this point. We've taken individual scores, we've turned them to z-scores, and then talked about them in terms of percentiles, and that's all relative to the population. The other thing that we want to do with z-scores is to be able to compare scores from different populations. So sometimes what we're comparing isn't measured exactly the same way. And so, for example, if we wanted to compare dollars spent dining to time spent shopping, then we couldn't do that directly because dollars and time is on two separate units of measurement. So they're not directly comparable. It's like comparing apples to oranges. However, if we know population information, in particular the means and the standard deviations, then we can standardize those measurements, turn them to z-scores, and compare them directly in terms of z-scores or standardized units. So let's go ahead and take what we know and let's walk through a particular scenario or a context. And so let's say we want to compare two 1-year-olds, Joey and Susie. We want to compare them on each other's development. And so we know going in, so maybe Joey's been measured before and Susie's been measured before, and we know that Joey has a score of a 7 on a quality of walking scale. And so it's a scale of 1 to 10, and he scores a 7 on it. And we also know that Susie can say 10 words. And so what we want to know is which 1-year-old is more developed. Now, given the information in this scenario right here, there's not much we can say because the two different measurements are on different units of measure. And so we have a scale of 1 to 10, and we have a count of number of words. And so they're not directly comparable. But if we have some means and some standard deviations, then we can convert this information to z-scores and make that comparison and determine maybe which one of these two children are more developed. So again, if we know the means and the standard deviations in the populations, then we can compare with z-scores. And so let's go ahead and just give some numbers for means and standard deviations. And so we'll use norm data. So not every single child that has ever existed has been measured on walking and talking, but we have enough and a diverse enough samples that we can go ahead and norm it. So let's say for walking on this 1 to 10 scale, that the norm is a measure of 4.21, so that's the average in the population, that's represented by mu. And then sigma, the standard deviation, is 1.75 scores. So we have Joey, he's given a score of 7 on this walking scale. We compare it to the norm of the population of 4.21 for the average, and a standard deviation of 1.75. We can do the same thing for Susie, and so we can take her 10 words that she can speak at 1 year old, and we can compare it to the norm of the population for 1-year-olds, and we see that on average children speak 6.42 words as 1-year-olds, and with a standard deviation of 2.32 words. And so we can convert both of these to z-scores. So go ahead and pause the video and use your formula that you learned in the previous segment, and go ahead and convert these to z-scores. Now, if you had used the z-score formula, you would have took Joey's score of 7 on the walking scale. You would have subtracted 4.21, that's the population average. You would have got a difference of 2.79. You would have then divided by 1.75, and you should have got a z-score of 1.59 for Joey. Alright, so let's take a look at Susie. If you had used the formula, you would have taken her score of 10 words spoken, subtracted the average of 6.42, you would have had a difference of 3.58, and then divide by 2.32, which is the standard deviation, and you should have got a z-score of 1.54. So hopefully those both check out for you. Alright, so based on the z-scores, it looks like that Joey may be just a little bit more developed than Susie. The numbers are fairly close together, and so maybe we want to get just a little bit more information to really make a better informed decision. In other words, to gather more evidence before deciding which one is more developed. And so we may decide to go ahead and calculate their percentiles. So we know there's a slight z-score difference. We may wonder if there is a percentile difference because those two z-scores are pretty similar to each other. So again, using the table and what you learned from the last segment of this lecture, go ahead and calculate the percentiles for Joey and Susie. So go ahead and pause the video and calculate their percentiles. So if you notice that their z-scores were both positive, so that tells you something right there. If they're positive z-scores, then you know that they're going to be greater than the 50th percentile. So if they have a positive z-score, you know you're past the average of the populations in the positive direction, and so you know it's going to be higher than the 50th percentile. So what you need to find on your table is the percent from the mean of 0 to the z-score for each one of our children. So a z-score of 1.59 for Joey and a z-score of 1.54 for Susie. And if you did that, you would have found that once you found that section, that percent between the value of 0 and their z-scores, that they would have ended up with the same percentile. So you take that percent, added 50%, turn it to a percentile while getting rid of the decimal place, and you would have found that Joey's percentile is the 94th percentile, and so is Susie's percentile. It's also the 94th percentile. Also, if you consider their z-scores and how they're categorized, remember they both had positive z-scores. Joey's was 1.59, Susie's was 1.54. Both of those scores fall within the above average range. So you remember we talked about we can categorize the normal distribution, and scores between 1 and 2z are what we would call above average. And so even though there is a slight advantage to Joey's z-score, slightly higher than Susie's in this particular case, the percentiles are the same, and they're both being categorized as above average. But when it comes to exams and worksheets, I don't want you to tell me that they're the same, because qualitatively they're actually quite different from each other. So we've calculated several evidences. We have z-scores, we have percentiles, we have a categorization to the normal distribution, but we can also talk about the reliability and validity of the measures. And so on an exam, you're going to be asked to give a practical decision. And in this practical decision, I want you to make a decision. So if you're asked which child is more developed, then I want you to tell me either Joey or Susie. Then I want you to give me the evidence of why you say that. So again, this is practice and critical thinking and supporting arguments that we talked about at the beginning of the semester, that there's always a chance that we're wrong with statistics, and so we need to support our answers with the evidences that we gather. So maybe you say Joey is more developed, and maybe you base that on the fact that he has a slightly higher z-score. So even though the percentiles are the same and we categorize Joey and Susie the same, we might say that Joey has a slightly higher z-score. We probably want to give another evidence as well. I'm looking for two evidences in your answers. So one, we could talk about the z-score is slightly higher. We can also talk about the reliability of their measurements. So if you remember back to their standard deviations, the standard deviation for Joey's population was 1.75. The standard deviation for Susie's population was 2.32. There is more variability with Susie's population. In other words, the values are less consistent, and we value consistency. So maybe we argue for Joey. We say because of his z-score is slightly higher than Susie's, and because his measure that he's measured on, the walking scale, is more reliable, then maybe we go with Joey and we say he's more developed. Now again, it doesn't matter to me who you decide on, as long as you support your decision. So we can also create an argument for Susie. So even though, again, Susie had a slightly lower z-score than Joey, meaning that she's just slightly more developed based on the z-score, we can argue and say that she still fell within the same percentile, she's still categorized as above average, and then we can also talk about the validity of the measures. That maybe counting the number of words is a more valid indicator of development than a 7 on a 10-point scale is. So in other words, we might say that counting the number of words is less subjective than creating a number on a scale of 1 to 10, which may be more subjective. So maybe Susie's measure is more objective than Joey's, in which case we may make an argument for Susie. So again, it doesn't matter to me who you say, Joey or Susie. Just support your argument with the evidence you have collected. Maybe that's the z-scores, maybe it's the categorization on the normal distribution, maybe it's the percentiles, maybe it's the reliability of the measures, maybe it's the validity of the measures, but give me at least two evidences that support your decision. So make a decision and then support it. So to summarize what we've learned in this module, the whole purpose of z-scores is to find more information about individuals by calculating z-scores to be able to compare to the overall population. How do they relate to the population? How relative is their score to the population? And then also to compare individuals across multiple unrelated constructs or across populations. So we can compare things like walking and talking. And again, we can do that as long as we standardize our measurements beforehand and standardize our values.